Okay, so good morning, everyone. We're going to start with the recitation number 2. So this one is basically more on how to write your first deep learning code. So far, through the previous recitations, you have seen foundations of Python, foundations of NumPy, and basics of linear algebra. By the way, if you cannot hear me, just let me know. No? Oh, my. Okay. So far in the recitations, in the previous recitations, you have seen foundations of Python, foundations of NumPy, and basics of linear algebra, right? And you also have seen through the lectures, like what is a neural network and what it can model. So today we are going to start writing, learning how to write the deep learning code. And this is like the overview of what we are going to see today. Yes. No? Okay. It's just voice projection. So these are like the main topics that we are going to see today. And we're going to start like with deep learning frameworks. So by the way, if you haven't had like the material yet, we can start like with the logistics. So you will have the material. It's like the tutorial PyTorch, the MNIST example, those 3 notebooks, and these slides in the course page. Can you hear me? Let's see. And also, well, we will have to take some little bit of advance in the lectures regarding the some of the topics that we are going to see today. And well, we can start with deep learning frameworks. So the first thing is, so what do they provide? What kind of computations you can do? The GPU support that you can get, some of the basic neural layers that you can get or combine with your models, and tools that you can tools to train your models. Also, ways to enforce general ways of coding your models, and most importantly than everything else is if they provide automatic backpropagation. So the first, so let's start with the frameworks. We have TensorFlow, which is developed by Google. And well, I classify these frameworks based on the main purpose that they have, the user friendliness, and the performance that they provide also. So TensorFlow, developed by Google, and the main thing that it's very high in computer efficiency, hard to get used to it, and the main purpose, well, it's widely used, and it can be used for many different things like data visualization. The only part of it is that it has like a static computation graph, which means that you have to develop that first before you can have like you can come in.
So it's more of like a compiled language where you compile the code first, and then when you are actually executing it, there is not you don't have a lot of freedom in changing that graph. Whereas in PyTorch, which we'll be using for this class, it's more like runtime. So the graph is built up dynamically, and you have a lot of freedom in the things that you want to change in it.
So for Keras, it's also high performance efficiency, but it's mostly like an interface for other frameworks, such as TensorFlow and Theano. So this is the easiest one. And then it's usually used for fast experimentation. If you want to do like a publication or something fast, Keras will be the one. And then DINET, it's usually used for natural language processing. It's also high in performance. And by the way, this one is developed by someone at CMU and their group. And then we also have Cafe, which is used for, the main use is for image processing. It's also high efficient when processing images, when computer vision basically, but not so much for natural language processing and recurrent neural networks. And then we have also deep learning G4, 4J, which is mainly used for distributed frameworks, just like Spark and Hadoop. And it performs similar to Caffe. So, and then the next one is Tiano, which is used for CNNs and RNNs, also used as a backend for Keras, just like I mentioned before. And it has a moderate speed. One thing about Tiano is like this is one of the first frameworks, and has been a little bit discontinued in the updates that they do. And then, of course, the one that we are going to be using throughout the course. Yes. Yes. Sorry about that. So the one that we are going to be using throughout the semester is PyTorch. One for because it's good in performance computations, and also it's easier than TensorFlow, and it contains dynamic computational graphs, and you can do automatic backpropagation. So we recommend for this class to use PyTorch 0.4 or PyTorch 1.0. And well, let's get started with this thing. So the next thing is a review of tensors. And you have seen already math, linear algebra, and indexing and slicing through the recitation 0 to A, 0A to 0Z, right? And then some of the data operations with PyTorch. So you can use, well, we will be using torch float tensor and torch float int tensor. And well, the first line show you how to create an initialized tensor. And then, as you can see, well, it's similar to NumPy. And then you can also convert a NumPy array to a tensor using the next lines. And then you can also export a tensor as a NumPy array using the command .numpy. And some of the basic operations that you can have are the following. Oh, oops. So you can also do like, yes?
What is the difference between a NumPy array and a tensor?
I think that also was explained on Recitation B, 0B. So it's like a 3D matrix. That's what it is.
For a tensor, you can store a lot more information than you can for a NumPy array. As you keep going, so you build your network and then you pass your input data, which is in form of a tensor, and then a PyTorch will automatically store a lot of information about that tensor as it goes through the network. So when we do backpropagation, we need to build this graph of sorts, and PyTorch automatically does that for us. So it will store the gradient values for a particular variable as it steps through the network, and a lot more. So you cannot do that with NumPy, but tensors allow you to do that. Like tensor stores that information.
Are the data types the same, NumPy and
Yeah.
like the precision would be the same?
Yeah. So the question was, are data types the same in NumPy and tensors? They are. You'll have like you have NumPy
Ints and floats.
in 32, in 64. You'll have the same thing in.
You actually can define that. Yes.
No,
in 32,
can I
in
expect
64.
the float 64 in PyTorch to have the same value as that in a NumPy float 64?
Yeah.
Yes.
Yeah, they are the same.
So when you can also do matrix multiplication with tensors, and well, now CPUs and GPUs. That's the next one. You can also. Oh. Why is going? Okay, here it is. So just like I said before, you can create tensors. you can copy let's see, a tensor from the CPU to a GPU using the CUDA command. So like this one, x.CUDA, and or you can copy the tensor from CUDA to CPU just using the .cpu. And also you can verify where the value is, if it's in GPU or in the CPU by trying this. And this is actually the error that if the value is not in the GPU, it will throw an error. I mean, it will throw an error if you don't have a GPU in your computer.
Also, this is about that there are certain operations that you cannot perform on the G. So there are certain operations that you cannot perform on the GPU. For example, if there is a CUDA tensor, you cannot convert it to NumPy directly. You have to copy it to the CPU first. So if you try, like over here in this example, you initialize X, so that is on CPU, and then you say Y is the X tensor on the GPU. And when you try to do y.numpy, it throws an error because it's a tensor on CUDA, but you're trying to convert it to NumPy. That's why you get this error. So, like, these are very small things that you should keep in mind when you're writing your code. Otherwise, you'll waste a lot of your time. Like, just keep these things in mind. So, there's like, this is a very basic operation that you might end up using a lot, converting tensors to NumPy, NumPy to tensors, but you cannot but you cannot convert a CUDA tensor to NumPy. You have to copy it to CPU.
So one more thing is that. One more thing is that.
So the question is there any reason for that as to why we cannot do certain operations on the GPU? I don't know all the details about it, but it has things to do with how you access memory, and where how some operations are performed and what kind of memory they need to access. It's somewhere around those lines. I don't know all the details about it. I can get back to you on Piazza. Thank you.
Forget now. So one other thing that you have to keep in mind is, just like she mentioned, like the operations between GPU and CPU. So you have to be mindful of that part. And well, if you have like a tensor in CPU and then a tensor in GPU, you cannot do like an operation combining both devices. So this will throw you an error actually. So just like this one, trying to do a multiplication of a CPU tensor with a GPU tensor won't work. So in order to have those operations valid, they have to be either in GPU or in CPU, both. That way the code will work fine. Okay, so the one thing that we are actually advancing in, this was mentioned slightly in last Wednesday, but you will see it in more detail next week, is the backpropagation part. So, So for the backpropagation, you will be seeing like the gradient descent, which is something that you have been seeing that during Wednesday, and you can go there. Yes. So go ahead.
Okay. So we haven't covered backpropagation yet, and we'll be covering it next week. But on the lecture on Wednesday, we talked a little bit about gradients and how do we learn a neural network. So you take an input and you pass it through your neural network. You compute the output of the neural network and compare it with the ground truth value, and that is how you get a loss. And now you get the derivative of this loss with respect to the parameters of the network, and using those derivatives we update our parameters, and we do this repeatedly iteratively, and that's how we learn the neural network. This when we are computing the output of the neural network, that is called the forward pass through the network. And after calculating the derivatives, when we go back into the network and update the parameters, that is known as backpropagation. We'll see all the details of it, all the math and the calculus behind it in the coming up lectures. But the good thing is that PyTorch saves us from the misery of writing that code and updating like keeping a track of the gradients. It does it for us, and that's why we say that PyTorch provides us with automatic differentiation or automatic backpropagation. We don't have to write the code for that explicitly. And okay, so all we need to do is do dot backward. That's it. And PyTorch does it all for us. We define our network. We define like the loss functions and other things that we'll see in subsequent slides. And eventually, at the end, when we are done with the forward pass, all we need to do is dot backward, and PyTorch does it for us. Can you go back? Yeah, so over here, yeah, so in this example, one thing to keep in mind is to calculate gradients. The variable for which you're trying to calculate a gradient of has to be of floating type. If it's a discrete value, you're not going to get a derivative of it. So all the the inputs that we are going to be sending in through the network or the network parameters, they're all going to be floating types. So here in this example, we define a tensor X, which is torch.arange. So you are basically going to get discrete integer type values. And when you set requires grad equals to true, you're trying to tell that you want to calculate derivatives for it. And so the tensor should store, should compute a derivative function for this particular tensor. But as expected, you're going to get an error because it is of integer type and it is not going to have gradient. So it is not going to, it's not a valid operation when you say that you want to compute a gradient function for it. And that's the error you're going to get. So the takeaway is keeping in mind that all the parameters or the inputs that we are going to be calculating derivatives with respect to should be floating type. And now suppose you want to, so there's this variable y, which we're saying is a function of x, it's x square. And we want to compute derivatives of y. So for that, we need x, we said that we make requires grad equals to false because we cannot have its gradient function. So we set that as false and we move on, we define y as x square. And now when we do dot backward on y, because it's a function of x, y is also going to have discrete values. And moreover, we said that x is not going to have a derivative function. So y is in turn not going to have a derivative function. So when you try to do this, again, you're going to get an error that you don't have the gradient function because x was discrete. So if you wanted to compute the derivatives of y, what you would do is convert the x tensor into a floating point, into a floating tensor first, and then set its required gradient as true. And now when you make y as a function of x square and you do y dot backward, you're going to get the values. Like when we print it out, we can see that we are able to get all the things that we wanted to get in the first place. Any questions? Okay, so here, starting now, we are going to look at some of the neural network modules that PyTorch provides us. Think of them as basic building blocks that we are going to use to build up our entire neural network and the entire pipeline to load the data, train it. So the first thing is, we all know that what a neural network is. It is basically a large number of parameters. And it can, if built properly and if trained properly, has the potential of learning anything. And PyTorch provides us a base class called torch.nn.module, which we will be using to implement our neural network. And it also provides us with a lot of predefined, like I said, basic building blocks to build these networks. So one of them is like, we've seen multi-layer perceptron. So it has multiple linear layers. So PyTorch provides us with a built-in linear layer module, which is also of torch.nn.module type. So if our network was just a single layer, you could define it like so. And to make a forward pass through the network, that is given an input, compute the corresponding output through the network. You just do dot forward. And if you want to access the values of all the parameters in the network, PyTorch provides us with this function dot parameters, using which you can access all the parameter values of the network. Because at the end of the day, neural network is nothing but the parameters that it is made up of. Any questions? Okay. So writing, we are going to look at some examples of how to write a very simple, basic multilayer perceptron. This is not a good way of defining your network, because what you're doing here is, if you look at the right side, so let's look at self.layer1 underscore weight. So what we are doing is we are initializing random variables, and we are wrapping them in nn dot parameter and assigning them as weights. Similarly, we are initializing the biases and the weights for the next layer. Why is this a bad way of doing it? Because it's too complicated. You don't need to do this, because PyTorch has given you well-defined modules already, like we saw nn.linear. So there is no reason why we should be writing like this. And it is also, this way of writing is also extremely error prone. One thing to keep in mind is that all the neural network parameters that we want to learn, which means that we want to be updated, should be a parameter of the network. If something is not a parameter of the network, it is not going to get updated, and you will not end up learning what you want to learn. So here you have to explicitly wrap everything in an nn dot parameter. And then in the forward pass, also you are explicitly defining all the functions that you want to do, the matrix multiplication between the inputs and the weights, and then adding the biases to them. So we don't need to do this, and this is the worst way of writing your neural network. Don't do this. A better way of doing it is using the modules that PyTorch does provide us with. Like here, we are defining the linear layer using nn.linear, defining the sigmoid function using nn.sigmoid, and then in the forward function, we pass the input through all of these layers sequentially. So this is a much better way of writing your network than this. Don't do this. And one more thing to keep in mind is, over here, when you define an nn.linear module, it will have some parameters, right? The weights and the biases. And now you're wrapping this in a bigger NN, like your neural network module, which is also an nn.module inherited from an nn.module class. So everything that is a part of a submodule is automatically going to get absorbed into the network. So the parameters of the linear layer are going to become parameters of your network. And when you are training your network, these parameters will also get learned. And an even better way of writing it is, on the previous slide, we see that in the forward layer, forward function, we are passing the input sequentially through the layers that we've defined. Whereas in this, if we wrap it in an nn.sequential module, that is done for us automatically. You don't have to define it in the forward function. So basically, nn.sequential applies the layers one after the other in a sequential manner, and you don't have to explicitly do that. And also, so the modules that we looked at, they have been given to us by PyTorch, but you can also define modules of your own. So suppose that the network that you're defining is going to have blocks that are going to be repeated throughout the network. So instead of defining them again and again in your init function, when you're defining the architecture, you can define an nn.module of your own and call it again and again. So it would be equivalent to using PyTorch's nn.linear. You're not defining it again and again, and all. It's kind of like modularizing your code. Similarly, you can define a module of your own and use it in your architecture. So over here, they've defined a tiny block, and then we are using it like and also wrapping it in nn.sequential, so that you don't have to, in the forward function, explicitly mention that I made a first pass through block 1 and then a second pass through block 2. It is going to do it on its own. Any questions? Okay. So optimizations and losses. We have so far looked at how we define the architecture of our neural network. But how do we train it? For training, we need to define a loss function. We need to define an optimizer. There are a lot of loss functions depending on what you're trying to achieve. What kind of data is it? Is it a regression problem? Is it a classification problem? Based on that, you'll have different kinds of loss functions. And there are also different kinds of optimizers like Adam, stochastic gradient descent. All of these we're going to look at in the lectures. But the good thing is, again, we don't have to write the logic, the code for our loss functions or the optimizers. The most commonly used loss functions and optimizers, PyTorch already provides us classes to implement them. We can inherit it and write our code and be good, and then we don't have to worry about back propagating through that loss, because PyTorch keeps, like, it builds up that graph and it keeps the information about the gradients with respect to everything. So it makes our life a lot easier. So here we see an example of using the cross entropy loss function. So you use, I don't remember the class exactly, I think it's torch.nn.optimizers, and from that you can inherit, from that you can use cross entropy loss function. I'm sorry, not the optimizer class, sorry. This is the loss. Optimizers, here we see, so from torch.optim class, we're using SGD over here, stochastic gradient descent optimizer. And to the optimizer, you need to send all the parameters of the network that you want to update. So like we looked at in one of the earlier slides, to access the parameters of a network, you can do just dot parameters. So here, if you have not encapsulated all the parameters under one bigger module, you won't have access to all of them. So the thing to keep in mind is that when you're defining your architecture, everything is encapsulated in a bigger class. Otherwise, you'll have to explicitly pass everything to the optimizer over here. And then there are a lot of other parameters like the learning rate, other things that are not coming to my mind right now. But you can go through the documentation. You should go through the documentation of these things when you're implementing them to get a better understanding of how they work, what they need, what they give you. And to update our parameters, all we do is do dot step. What that does is the optimizer calculates the gradients of the loss function with respect to the parameters, and then it takes a step in the negative direction of the gradient by scaling it with the learning rate. We saw the basic idea of how parameters are updated, the gradient descent, in the lecture on Wednesday, and how backpropagation takes place. Like I mentioned before, it's going to be mentioned in the week starting Monday. One important thing to keep in mind is that the optimizer, during backpropagation, it accumulates the gradients. It does not reset them. That means when you are, so I hope that everyone knows that generally we make batches of our data and make updates after passing a batch of the data through the network. So suppose you pass one batch through the network and make an update, and now when you're passing the second batch of the data and make updates corresponding to the second batch, you need to make sure that the gradients that were computed using the first batch are cleared off. Otherwise, your gradients are going to keep on increasing and explode, and those are not even the gradients that we want to use during updation. So we need to zero out the gradients, and that can be done by either using optimizer.zerograd, and it is equivalent to doing net.zerograd. But we should keep in mind that we do this, and we usually do this at the beginning of our training loop. So this is very simple, that can give you an idea that if we are running it for say 100 iterations, you first reset the gradients, you calculate the output from the network, you compute the loss, and then you do loss.backward, and that will compute the gradients, and then you do optimizer.step to update your parameters of the network. Saving and loading, it's very important, and so you should be able to save your network and load it back at any point of time that you want. It'll happen that when you're training your networks, you might lose your connection to the EC2 server, and your training will just stop. To avoid that, we did mention using screens in one of the previous recitations. But for whatever reason, if you suppose you train for 11 epochs or 20 epochs, and then you lost connection, you are not able to recover your training, you'll have to start all over again. But we don't have to do that. We should be saving our networks, our neural network, and other things with it that we need to resume training. And we can do that by using torch.save. And like I mentioned before, a network is nothing but the parameters that is made up of, and those parameters can be accessed by using .stateDict function. So like in the first snippet of code, we see that we define a neural network which has two linear layers. That means we'll have two sets of weights and two sets of biases. And when we look at the state dictionary, we see that is it returns those keys to us. Using the state.dict function, you can access it. It basically creates this dictionary which has key value pairs for different parameters that you have for different parts of your network. So you can simply do torch.save, and if you're trying to save only your network state, then you do net.stateDict. And then when you want to resume training from a saved model, all you have to do is load it back and resume the training. So to load it back, you can use this function load stateDict. And over here on the slides, we've only mentioned how to save the dictionary or the state of the network, but there are many more things that you can save while you're saving your network to ease resuming the training, such as you can, when you're using optimizers, the optimizer will be in a particular state. You can save the state of the optimizer if you're using schedulers, which again, when you start working on homeworks, you'll realize they also are in a particular state, and you can save that as well. So please go through the documentations of these functions online. They'll help you understand how to use them to the best. Any questions? Okay. So we'll be covering some of the common issues that all of us run into, and if you keep them in mind, it'll be very easy for you to debug your code and avoid errors that can be completely avoided. So the first thing to keep in mind is not to perform operations on tensors, some of which are on GPU and some of which are on CPU. Everything has to be on the same machine. Otherwise, you're going to run into an error. Size mismatch during vector multiplication, obviously. It's mainly just matrix multiplications, and if the sizes are wrong, there would be an error, obviously. And in a PyTorch, the asterisk sign is not the same as matrix multiplication. It is element-wise multiplication, as you can see in this example. I'm sorry. When you've defined x and y, if you use the asterisk sign, it is element-wise multiplication. And when you do matrix multiplication, you see it's a different value. So please don't mistake the asterisk for the matrix multiplication operations. Also, .view. We use this function a lot, but it is not the same as taking the transpose of a matrix. .view is just kind of visualizing the data that you have in a different format. It doesn't change the structure of the data. So in this example, you can see that .transpose and .view give you two different data, two different tensors. They cannot be used interchangeably. Broadcasting. When you are trying to perform operations, I mean, this is the same as NumPy. Something to keep in mind if you are using, if there are operations that can be performed with tensors of different sizes, but they are not broadcastable, you're going to run into an error. Like very basic things to keep in mind, very much similar to NumPy as well. GPU memory error. So your graphic unit is going to have a certain capacity of the data it can hold at a time. If you are trying to load a lot more data than it can hold, you're going to run into a CUDA memory issue. All of us are going to run into this issue throughout the duration of the course. When you try to feed a batch to the GPU, and on your terminal you see this scary message written out that says CUDA memory issue in caps. It's basically you're trying to put in a lot more data than the graphic unit can hold. In this example, we've defined an insanely large, insanely huge tensors, and if we ran it, it would run into a CUDA memory issue. So whenever that happens, make sure that you're clearing out your cache, you're using smaller batch sizes, things like that. Keep being mindful of what your graphic unit supports. Okay, so looking at this example, do you think anything is wrong with it? Is it correct? Floating point? Correct. So if we ran this, we'd run into this error because the x should be a floating point, a floating tensor. The reason, like I mentioned before, the parameters are all going to be floating type, and there have to be matrix multiplications to calculate the output. And when your parameters are of floating type and your input is of long type, when you try to do a matrix multiplication, you're going to run into an error. over here, do you think anything is wrong with the snippet of code? It is in the init function. If there is something wrong, it's in the init function. Okay, another hint, it has got something to do with how parameters are updated, what parameters are updated. Anyone? So you see how we are trying to initialize a list, and then we are appending linear layers to that list. But this list itself is not a module. It's not going to get absorbed into the network. So all the linear layers that you're appending to this will never get updated. They will not become a part of your network, and they will not get updated. So whenever you are doing such an operation, appending modules to a list, make sure that they are a part of the network itself. So like it's mentioned here, the hidden layers are not module parameters. They will not get optimized. So how do you make them a part of the module? By using nn.module list. There are other ways as well, but this is one of them. You could have simply used nn.sequential as well and unpacked your list. So now your nn.sequential would have all the linear modules that you'd appended into your list. The key thing to take away from this example is to make sure that everything that you want to be updated that is a part of your neural network is updatable. That is, it is a part of the module. Yeah. So the final layer is nn. It's not a part of a list, right? It is an nn.module of nn.module class. But when you put all these other nn.linears in a list, now it is, although it is there in the init function, it is not associated with the rest of the nn.module classes. Yeah. Any other questions? Yeah. It is going to give you an error. Yeah. Yes, exactly. Exactly. Any other questions? Okay. Some very basic debugging suggestions. Try to debug, whenever you run into an error, try to debug it yourself. If something looks absolutely crazy, absolutely unexpected, try printing out your inputs, your outputs, intermediate parameters, look at the errors. They are helpful most of the time. You can use the debugger. In one of the recitations, we've explained in great detail on how to use debugger in Python. All you have to do is import PDB and then use pdb.setTrace to set a breakpoint at whatever part of your code you want to stop, and then step through it. There's so much online resource available that almost every error that you're going to run into, you're going to find it on Stack Exchange or someplace else, and they're helpful most of the time. But if there's something that you're not able to figure out at all, you can post it on Piazza. Be mindful that whenever you're having issues with your code and you are trying to post your code, make it as a private post. But if it is some generic question which does not involve the need for your code, make it a public post so that anyone else who runs into the same issue can benefit from it. And whenever you're posting on Piazza, please go through the posts that are already there, because most of the times there are a lot of issues that are very common. Almost all of us run into them. So somebody might have already asked them on Piazza, and you can find a solution much faster than if you make your own separate post. And if nothing helps, please come see us during the office hours. Okay, till now we saw like parts of basic building blocks that help us to build a neural network, help us to train it. And now we'll look at an example code, which is end-to-end. We'll load the data, we'll define the network, and we'll train it. If you want, the material, like the notebook is there on the website. If you want to step through it with me, you can open it on your systems right now. Or you can just look at it here. Is the text big enough for everyone to see? At the back? Okay. So for this example, we are going to be looking at the MNIST dataset. Almost all of us must have heard of the MNIST dataset. It's like the hello world of deep learning. If not, then it has 60,000 training samples, 10,000 testing samples, and it is basically just a bunch of handwritten digits from 0 to 9. And they're 28 by 28 in size, grayscale images. So the first thing we'll do is import all, like in any code, import all the requisite libraries. So we import NumPy, we import torch libraries. We are importing the NN module, functional module, optimizer. Then there's the data library that we use for the data loader and the dataset class, which we'll look at in this code. And then there's Torch Vision, which is mainly used for computer vision applications. We will probably not use that much in this course, but it's good to know about it. Then Matplotlib to visualize some of the stuff, and timing for profiling our code. We see that right now we're running. If you don't have a GPU on your machine, it will run, but it'll be super slow. Also, one more thing before I proceed. Always write your code such that it runs both on CPU and GPU, that you don't have to make changes when you transfer your code from your CPU to your GPU, because when you'll be writing your code, when you'll be debugging it, you'll mostly be doing it on your machines. You should be doing it on your machines, that is on the CPU. And when you're ready for training, that is when you should put it on the GPU and start training to save your credits. So if you have to make changes in your code to make it machine compatible, that is going to be a lot of hard work. So you should always make your code such that it can run on any of the machines, like be it CPU, be it GPU, so that you don't have to make changes to your code. So right now we see that we'll be working on a GPU. So we used MNIST class over here to download the data and just do a basic profiling of what our data looks like. And we see that our data has 60,000 training samples, which are 28 by 28, and 10. Oopsie, this should be test, and that'll be 10,000. Yeah, so 10,000 test samples. And just to get an idea of what our data looks like, we'll visualize some of the samples. So here we visualize the first training sample. It looks like a 5, and the ground truth label is also 5. One more, just for the heck of it, 0. The ground truth label is 0. And now the data loader. This is extremely important, and you should all pay great attention to it. So usually we are working with really huge amounts of data where we have millions and hundreds of thousands of samples, and you cannot feed all your data into the network at a go. And that is not even a good thing. Like all of you, I'm hoping know that we generally batchify our data, like I mentioned before, and pass batches of the data through the network and make updates after each batch. So in order to get this batch of the data, we use the data loader and the dataset class in PyTorch. So the idea is that we pass our dataset into the data loader, and it returns batches, iterable batches to us. And in order to pass the data into the data loader, we make use of the dataset class. So here, what you see in the first cell is how I've defined the dataset class for this particular example. So the dataset class has 3 important functions: the init function, the len function, and the get item function. If we understand the functionality of what we are trying to achieve from these functions, no matter how complicated your data is, no matter what you want to do with it, it's very easy to implement it. But it's really important to understand this well. Otherwise, you don't have any option actually. You need to understand this well. So in the init function, you send into the class the data or any additional parameters that you will be using. And in the init function, like any other class, you set them as the class attributes so that you can use them in the subsequent functions. What the len function does is it returns you how many total samples you've sent to the class. So over here, if we are training it this training data, if we're sending the class a training data, we know that we have 60,000 samples, so it should return 60,000. This is to get like for subsequent operations, knowing how many samples of the data you have. That is what your len function should return. What the get item function does is it samples a point from the data that you've sent it, and you do any pre-processing that you want to do with the data and return it from the get item function. So you'll get an index value which, based on whether you want to shuffle your data or not, it will be a random value or a sequential value, and then you index into your data and the corresponding labels and return them. In this particular case, we saw that our input data is of shape 28 by 28 because they're images. And we are going to be using a multi-layer perceptron in this example. And for a multi-layer perceptron, we need you're not going to feed an image into the multi-layer perceptron. You need a one-dimensional data. So for that, we are reshaping the data here. So your data should look like 1 cross, or without a dimension here, 1 cross 786, 28 and 28, I think. And over here, I have converted the input data into a float type tensor and the corresponding labels into long type, because we are trying to do a classification here. We are trying to classify each image into one of the 10 classes 0 to 9. So your ground truth labels should be long type. They should be integer, discrete. And then we return it from the get item function. In this snippet of code, we are defining a data loader for both the train and test data sets. So first, you see at line number 4, we define a train data set for the training data. The class that we define here, my data set, we send it the training data and the labels. And then we define some arguments for the data loader. You could have mentioned them while declaring the data loader itself, but it's easier practice to like define this dictionary. You can reuse this code whenever you are working on your homeworks. It's just an easier way and a cleaner way of doing things. So you have parameters which allow you to do multiple operations with your data, like do you want to shuffle your data or not? The batch size, that is how many samples do you want to be there in a single batch? Number of workers, that is, this allows you to process generate batches in parallel. So the data is going to be huge, your neural network is going to be huge, it is going to take up time. What you do not want is that your data generation become a bottleneck to the subsequent actions. We know that that is going to take time. We don't want our data generation to take time. So this allows us to parallelize that. And then you pass these arguments and the data set for the training data into the data loader class, as you can see on line 8. And we do the same thing for testing. And now this train loader on line 8 and the test loader on line 15, these are iterable. We can iterate them and get batches of data, batches of training data and batches of test data. And further down to the code, we'll see how we use them. Does anyone have questions related to the dataset class about any of the functions? Yeah. Yeah, so this is actually particular to this machine. I've never used this line before when I write my code. For this particular machine, I needed to make sure that depending on whether it is running on a CPU or on a GPU, I need to define different numbers. Because when it's running on a GPU, I can process more, so I set it as 2. And when it's on the CPU, I cannot do multiple processing, so I set it as 0. Yeah. 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 Okay. So the question is, I mentioned that we should write a code such that the code is compatible with both CPU and GPU, and is this how we do it? We have not yet sent anything onto the GPU or into the CPU. Everything at this point of time is on the CPU. We'll see further down how we make sure that our code is compatible. Basically, do you remember in one of the earlier slides we saw .CUDA and .CPU commands to move data to CPU and GPU. We should not do that, because if you have written in your code .CUDA, you'll have to change that. We use commands like moving .to device, and this device will be a string which will either be CPU and GPU, and we'll set that string based on the available, like by checking what machine it is. We'll see it. Actually, no. So here we will see it. I mean, on line 15, you see we are checking what machine we are on. So CUDA is true. So we have, if CUDA is true, I'm going to set a string called device as CUDA. And if this was false, I would set it as CPU. And then I would move my data by using .to and device. So that way, depending on what machine it is on, that is what the data is going to get moved on. Did that make sense? Any other questions? Yeah. Okay. So the class, yeah. Can you repeat that question? Sorry. Yeah, you need to implement that. The len function should return how many samples that particular data that you sent it to has, so that it knows how many times it needs to sample. And if suppose your data had, so right now we have 60,000 training samples, and if the len function was not returning 60,000 and say it was returning 65,000, so in your get item function, the index is going to get sampled from range 0 to 65,000. And then you're going to try and index into your data set with an index that does not exist, and you're going to run into an error. So this is for the ease of, this is for sampling data from your data set. So the len function, all it is supposed to do is return the length of your data set. And then in get item, you sample it using that index and do whatever pre-processing that you want to do with it. Any other questions? Okay. So now we move on to defining a neural network that we'll be using for this particular problem. We are using a very simple multi-layer perceptron. Like I mentioned before, we are using a list to hold multiple linear layers in it. And like we saw before, earlier we used nn.module list to pack the list in a module class. Over here, we are unpacking the list in an nn.sequential. So you can use either of them. The important thing is to keep in mind that they are all a part of the module class. Otherwise, they won't get updated. And by defining it, so in the forward function, actually, we didn't even need to do that, but yeah, that's what we did. No, it's not a pointer to layers. So layers is a list, and by doing this asterisk layer, you are unpacking the list into nn.sequential. It's not a pointer. So it's an yeah. So you have these layers. Printing them out individually is different, but if they are packed in a list, they are a part of a list, right? You need nn.sequential doesn't need a list. It needs the parameters that you want to make sequential. So it's just a way of writing it. You could have written nn.sequential and in brackets everything that you've written above that, or you could do like this is just to give you different ways of writing your code to make it compatible. Correct. Yeah, because you're not unpacking a list then. You are telling that this list is a module class. Yes. This is just the definition of a class. I mean, I don't know what to explain about that. Yeah. You're basically just instantiating the class. Any other questions? Okay, moving forward. So now we've defined our data loader. We know how to get batches of our data. We've defined our model. Now we're going to look at how we define the loss function and the optimizer. So we define this class simple MLP for our neural network. We pass it the required parameters, get our network. We are going to be using cross entropy loss, and we'll use Adam optimizer for this particular problem. And like, you need to send in the parameters of your model to the optimizer for it to know what to update. So we do model.parameters in the optimizer, and then we get what device we are going to be working on at line 4. We, based on whether CUDA is available or not, we set the device as CUDA or CPU. And you could just print your model and see what your model actually looks like. So here we can see that we have 2 linear layers with the ReLU activation. Now we are going to write any questions about this? Yeah. You mean NN dot parameter? No. So the question is that earlier we had seen the usage of NN dot parameter to make things parameter of a network, and here we haven't mentioned that. So is it done? Do we need to do explicitly, or is it done implicitly? So you see how in the how while defining the network we used NN dot linear, which is a module class. So and then we made them a part of another class, which is our network, which is also a module class. So I had mentioned this before. I'll mention it again. Everything that is a module class and is a part of your network, is their parameters are going to get absorbed into the network parameters. They will automatically become a part of the network and get updated. If you put them in a list, then it won't be a part of the network, and you have to use, like over here we are using NN.sequential unpacking the list here, or in the previous example we had seen using NN.module list. So if you're putting it in a list or something that is not a module class, you need to explicitly make sure that you're doing it. Otherwise, for the classes that PyTorch gives us, which are already module, you don't need to do that explicitly. So everything that is going to be a part of both of these NN linear layers are automatically going to become a part of your network. And over here at line 3, when you do model.parameters, all of them are going to be sent to the optimizer. Any other questions? Okay. So now we'll write a simple training loop. We write a function to which we are sending our model, our training data, our data loader for the training data set, the criterion, and the optimizer. The criterion here is the loss function. So you see, the first thing we do is set the model to training mode, because there are certain operations that we look further ahead into the course that have a different way of computing things based on whether you are evaluating your model or whether you're training your model. So first thing we do is set the model to the training mode. Then we move our model to a device, whichever it is. At this point of time, it will get moved to the GPU because this code is running on the GPU. Then you initialize this variable to keep a track of your loss. It's a good idea to keep a track of your loss, helps you debug. And then at line 8, we start iterating through our data loader. So when I do this, what it is going to return is a batch index, because we're using enumerate, and data and target is going to be returned by the train loader, the data loader that we defined earlier for the training data. And then we are going to zero out our gradients by doing optimizer.zeroGrad. We could have also done model.zeroGrad. We move our data to the device, we move our targets to the device, and then we compute the output of the network simply by passing the data into the model. This will call the forward function and compute the output of the network. Then we calculate our loss by passing the output that our model calculated and the ground truth values into the criterion. We update our variable that we had created for keeping a track of the loss. Then we do loss.backward. This is going to backpropagate the gradients through the network, and optimizer.step is going to update the parameters. This is mostly all, these are all the steps that you need to take. You need to make sure that your data and your model are on the same device. You pass your input through the network, you get the output, you compare it with the ground truth value, you get the loss, you compute the derivatives, and then you update your parameters. Simple. Do you have a question? So the loss.backward is going to compute the gradients, and optimizer.step is going to use those gradients to update the parameters using a particular algorithm based on what you choose your optimizer to be. Yes. Yeah. Because you need to get your gradient. So the question was, is this the particular sequence that we need to follow? First we do loss.backward and then we do optimizer.step. Yes, because you need to get the gradients first, and then only are you going to be able to update your parameters. Otherwise, you will be updating with wrong gradients. So the question is, does optimizer.zerograd run on each epoch or for each batch? Correct? Yeah. So you want to do it for each batch because you update your network parameters based on the data that you have seen. You make some updates, and then now you have a better version of your model. And now using more information, you're going to update it again. You want to zero out the gradients before making each update to the network. So we do it for each batch. Any other questions? Okay. So now we are going to write a simple testing or validation function. It's exactly the same as our training function. But we now set our model to the eval mode, because like I mentioned before, there are certain operations that are different in training and evaluation. So during evaluation, make sure that your model is in eval mode. We move a model to device. We initialize some variables to keep a track of things. And then we iterate through our test loader. We move our data and our targets to device. We calculate the output of the model. And then over here, because we are trying to classify each of the inputs into 10 classes, we are going to see which output has the highest maximum output, and that is the class that our model is trying to classify our model into. So we get the class that is classifying it into. This particular snippet of code from 16 to 19 is going to be different based on what you're trying to do with your code, based on what losses you're using, whether you're classifying, whether you're regressing. Based on that, it's going to be different. But here, because we're trying to do classification, this is this problem specific. Then we compute the loss, and yeah, that's it. Simple, mostly like the training loop, nothing new, except for keeping in mind that we set our model to eval mode. Any questions about this? Okay. And now we are going to call these functions for particular number of epochs to train our data and then validate. So here we've set the number of epochs to 10, and you see I call the training function that we defined at line 7, I call the testing function. This is kind of like validating. You want to validate after each epoch to see whether we never evaluate our data. I mean, we never say that our model is this good based on what it does on the training data. What matters is how it performs on unseen data. It should generalize well. It should learn how to do well on data it has not seen yet. So we always evaluate our model on validation data, testing data. The terms are used interchangeably in this particular code, test and validation, but test data is something that you never see. Here, test has been used for validation data. I hope that's not confusing. If that's not clear, please let me clarify it right now. Does anybody have any questions about that? Okay, good. Yeah. Mm-hmm. Okay, so the question is that we used a loader to create batches of our training data. And in each epoch, how do we make sure that we are looking at different data? These are very different things. When you are trained, like in this training loop, you have 60,000 samples. In each epoch, your network is going to see each and every one of those 60,000 samples. But each of these batches are going to be independent. So during one training epoch, no sample is going to be repeated. Any other questions? Okay. So this is, we calculate our training losses, we calculate our testing losses and accuracy. And then we just visualize it to see how it's doing. So we see that the training loss stagnated after some time and the validation loss started going up. So we got our best model somewhere around the 50 epoch. Simple. And the accuracy also obviously started decaying after that. So this code shows you how to use a data loader to create batches from your data, how to create an architecture, how to write a training loop, how to write a testing loop, and put it all together to train your network for however many epochs you want to train it. Yeah.
In the training group,
Mm-hmm.
before we start with training model dot train
Yeah.
for every epoch, right?
Yeah.
Why do you need to send it to the GPU? Like, don't the one sample is residing in GPU wants to do a dot two device?
Are you asking about dot train or dot to
I'm
device?
asking about dot two device.
Okay.
Why do you send the sample to GPU originally? Because now it is
Okay. So the question is, why are we doing model.gpu in every epoch? You could, I think, for this particular code, move it out because we are not making any changes. So we can do model.toDevice only once before we start going through all the epochs. But you need to set it to train mode for every epoch because you set it to .eval when you tested the epoch before. And your data has to be moved to device in each epoch for each batch, because if we do to device to the entire data, probably the data is going to be so huge that your unit is not even going to be able to hold it. So we send batches at a time. Model, yeah, you are right. Probably we could just have done it before.
before doing a model dot two device,
Uh-huh.
you decide to optimize it. So does that mean that the optimizer parameters are now in GPU, but the device parameters are in GPU, and they can now update in the model to the optimizer in GPU?
We never do optimizers or to device. No. We never do it. And your question confuses me as well. I'm definitely going to get back to you about this on Piazza. The question was the model and the data is we move it to the GPU, but the optimizer is on the CPU because we never did it to .gpu, and we update our parameters using the optimizer. So one thing is on GPU, other thing is on CPU. How does it work? I'm confused right now. I'll get back to you about this on Piazza. I saw a hand go up there. Do you have a question? Okay, good. Yeah. Yeah. So there are layers like batch normalization layers and dropout layers that we are going to be looking at further ahead into the course. They are different. The way you compute and output through those layers is different depending on whether you're training your model or whether you're evaluating your model. So you need to make sure that your model is in the correct mode. Otherwise, you would be doing wrong computations. It won't throw an error, but it will be wrong. And then you wouldn't know what's going wrong with your model. Yeah. Sorry. So the question is, does the optimizer have an alias to the model parameters? I don't think it has a copy of the parameters. We send to the optimizer the parameters themselves, which get updated. So there is no need for there to be a copy. I don't think there is a copy. Any other questions? Okay, so this is it for the recitation. And on the website, we have posted this notebook, the notebook from which we have taken snippets of the code that we presented in the presentation, but there's a lot more in that notebook. Please go through it because there are a lot more things that you're going to learn, a lot more issues that we've mentioned in the notebook. And there's one more very basic example. You can go through that material and it will help you understand how to better understand how to write your code, the issues that you're going to run into, how to resolve them. Please check out the material on the website. Any questions? Okay. Thank you. Thank you, everyone.